Hey there, curious minds. What if I told you that right now, as you're watching this video, another version of you is doing something completely different? Maybe that other you finally asked out their crush. Maybe they took that job in another city. Or maybe, and this is the fun one, they clicked on a different video and are now watching a cat compilation instead. Sounds like sci-fi nonsense, right? Well, here's the thing. Some of the smartest physicists on the planet are dead serious about this. We're talking parallel universes, and the evidence is getting harder to ignore. Today we're going on a wild ride from ancient Greek philosophers who accidentally predicted the multiverse while sitting around in togas, to quantum experiments that broke reality so hard that scientists had to invent infinite universes just to make the math work. We'll explore cosmic fingerprints that might be literal bruises from our universe bumping into others. Yeah, you heard that right. Universe fender benders. So before we shatter everything you thought you knew about reality, smash that like button if you're ready to have your mind properly blown, and drop a comment telling me where you're watching from. I want to know which corner of this universe is tuning in today. Ready to question everything? Let's dive in. Let's rewind the clock about 2,500 years, back to a time when Greece wasn't just famous for olive oil and questionable fashion choices involving bedsheets. This was the golden age of philosophy, when brilliant minds sat around asking the big questions about existence, reality, and why anything exists at all. And somewhere in this intellectual hotbed, two thinkers came up with an idea so ahead of its time that it makes most modern innovations look like someone reinventing the wheel. Except the wheel already existed, so even that comparison falls flat. Meet Leucippus and his student Democritus, the dynamic duo of ancient atomic theory. Now, we don't know much about Leucippus personally. In fact, we know so little that some historians have questioned whether he even existed at all, which is a pretty impressive level of obscurity. Imagine being so mysterious that people 2 millennia later are still debating if you were a real person, or just a really elaborate inside joke. But whether Leucippus was flesh and blood or the ancient equivalent of a pen name, his ideas were very real, and they would echo through the centuries in ways he could never have imagined. Democritus, on the other hand, left a much larger footprint on history. Known as the laughing philosopher because he apparently found human folly hilarious, which, fair point, have you seen humanity lately? Democritus took his teacher's ideas and ran with them like a marathon runner who just discovered energy drinks. Together, or perhaps in succession, these two developed a theory that would form the foundation for how we understand matter itself, atomism. Here's the basic pitch. Everything in the universe, according to Leucippus and Democritus, is made up of tiny, indivisible particles called atoms. The word atomos in Greek literally means uncuttable, which tells you everything you need to know about their concept. These atoms were the smallest possible units of matter, the fundamental building blocks of reality. You couldn't split them, you couldn't break them down further, and you definitely couldn't see them with the naked eye. They were just there, doing their atomic thing, combining and recombining to create everything from rocks to rivers, to that annoying neighbour who always borrows your tools and never returns them. Now, this might sound like basic chemistry to us today, and you might be wondering why this is relevant to parallel universes. After all, we learn about atoms in elementary school, right? Well, hold on to your toga, because here's where things get interesting. The ancient Greek concept of atoms was remarkably sophisticated for its time, but it was also wildly different from our modern understanding in some key ways. And one of those differences opens the door to a mind-bending implication about the nature of reality itself. Leucippus and Democritus didn't just propose that atoms existed. They proposed that atoms moved through an infinite void, an endless expanse of nothingness in which these tiny particles could zip around, collide, combine, and separate. This void wasn't just big. It wasn't just really, really big. It was infinite. Boundless, without limit or edge. Try to picture that for a moment. Actually don't, because your brain will start making that Windows error sound. The concept of true infinity is something humans are genuinely bad at grasping, which is probably why we invented finite things like pizza slices and Netflix episodes, though the latter is debatable when you're on your 5th hour of binge-watching. But Democritus didn't shy away from infinity. He embraced it with the enthusiasm of someone who just discovered an all-you-can-eat buffet. And here's where his reasoning takes a turn into multiverse territory. If the void is truly infinite, and if atoms are constantly moving and combining within this infinite space, then over infinite time, every possible combination of atoms must eventually occur, not might occur, not could occur, must occur. It's a mathematical certainty, or at least it seemed that way to Democritus, who unfortunately didn't have access to probability theory or a decent calculator. Think about it this way. If you had an infinite number of monkeys typing on an infinite number of typewriters for an infinite amount of time, eventually one of them would produce the complete works of Shakespeare. This is actually a famous thought experiment in probability, and while it's usually used to illustrate randomness and infinity, it applies perfectly to Democritus's atomic theory. Given infinite space, infinite atoms, and infinite time, every possible arrangement of matter would have to exist somewhere, including logically other worlds. Democritus explicitly stated this. He believed in the existence of countless worlds, some with suns and moons like ours, some without, some with life, some barren and empty. These worlds were born, grew, decayed, and died, only to have their atoms recycled into new worlds in an endless cosmic dance. This wasn't mysticism or poetry. This was, in Democritus's mind, pure logic following from his basic premises about atoms and void. If the raw materials are infinite and the space is infinite, then the products must be infinite too. Simple as that. Now let's pause and appreciate how absolutely bonkers this idea was in the context of ancient Greece. Most of Democritus's contemporaries believed the earth was the centre of everything, that the celestial bodies were divine or at least special, and that our world was unique in its existence. The idea that there might be other worlds out there, let alone infinite other worlds, was about as mainstream as suggesting that the king should maybe consider a democratic election. It just wasn't done. But Democritus didn't care about being mainstream. He was too busy laughing at human foolishness and thinking about atoms to worry about social acceptability. His ideas were preserved and passed down, though often criticised or misunderstood through the writings of later philosophers. Epicurus, who lived about a century after Democritus, adopted and adapted atomic theory, adding his own philosophical twists. The Roman poet Lucretius later wrote an entire epic poem called On the Nature of Things that laid out Epicurean physics in beautiful Latin verse, which is honestly a flex we don't see enough of in modern science communication. Imagine if Stephen Hawking had published A Brief History of Time in iambic pentameter. Actually, that would be amazing, and someone should do that. Through these channels, the atomic theory of Leucippus and Democritus survived the fall of ancient civilizations, the rise of new religions, and the occasional book burning that seems to be a recurring theme in human history. The idea of infinite worlds in infinite void never quite died, even when it went underground or got absorbed into other philosophical traditions. It was like a meme that refused to disappear, popping up in different forms across different cultures and centuries, always carrying that same basic kernel of truth. If the universe is truly infinite, then our world cannot be unique. Of course, Democritus got a lot of things wrong. His atoms weren't actually indivisible. We've since split them into protons, neutrons, and electrons, and then split those into quarks and leptons, and at this point we're not entirely sure if there's a bottom to this particular rabbit hole. His void wasn't quite the empty nothingness he imagined, since we now know that even empty space is filled with quantum fields and virtual particles popping in and out of existence like cosmic whack-a-mole. And his mechanism for how atoms combined, basically they had little hooks and grooves that fit together like ancient Lego bricks, was more imaginative than accurate. But here's the thing about being a pioneer. You don't have to be right about everything to be profoundly important. Democritus didn't have electron microscopes, particle accelerators, or even a basic periodic table. He figured out that matter was made of tiny particles through pure reasoning, sitting around in ancient Greece with nothing but his brain and perhaps some excellent wine. That's like figuring out how to build a smartphone by staring at a rock really hard. The fact that he got the broad strokes right is nothing short of remarkable. And his multiverse logic, while not scientifically rigorous by modern standards, captures something essential that modern physicists are still grappling with today. The argument from infinity, that if the universe is truly infinite, or if there are infinite parallel branches of reality, then every possibility must be realized somewhere, remains a central pillar of many multiverse theories. Democritus didn't have the mathematical framework to formalize this argument, but he grasped the intuitive core of it over 2,000 years before anyone else would take it seriously. It's worth noting that Democritus wasn't alone in thinking about multiple worlds in ancient times. Various cultures and traditions had their own cosmological ideas that included the possibility of other realms or dimensions. Hindu cosmology, for instance, describes vast cycles of creation and destruction across countless universes. Buddhist philosophy contemplates multiple world systems and realms of existence. Ancient Mesopotamian myths hinted at layered realities. The human imagination, it seems, has always been drawn to the idea that our world might not be all there is. But Democritus was unique in deriving this conclusion from a physical theory, rather than religious revelation or mythological tradition. His multiple worlds weren't the abodes of gods or the afterlife destinations of souls. They were just more worlds, made of the same atoms as ours, following the same natural laws, existing in the same infinite void. This was materialism taken to its logical extreme, and it scandalized pretty much everyone who heard it. The philosopher Plato reportedly wanted to burn all of Democritus's books, which is the ancient equivalent of trying to get someone cancelled on social media. Thankfully, enough copies survive that we still have access to his ideas, even if most of his original writings have been lost to time. The implications of Democritus's atomic multiverse are staggering when you really sit with them. If every possible combination of atoms must exist somewhere in the infinite void, then somewhere out there, in some distant corner of the endless expanse, there's another world almost exactly like ours. Another Earth with another Greece, with another philosopher named Democritus thinking about atoms. But maybe in that world Democritus decided to become a potter instead, and someone else came up with atomic theory. Or maybe no one did, and that world is still stuck thinking everything is made of earth, water, air, and fire, like a really basic elemental starter pack. The concept gets even weirder when you consider that, according to this logic, there could be infinite copies of you out there, living infinite variations of your life. In one version, you decided to watch a different video today. In another, you were born in a different century. In yet another, the atoms that make up your body combined slightly differently, and you're a completely different person with completely different thoughts. Or you're a frog. Infinity is weird like that. Now, Democritus didn't have the language of quantum mechanics or cosmological inflation to describe these ideas. He was working with thought experiments and logical deduction, not equations and empirical data. But the fact that modern physics has arrived at similar conclusions through completely different methods is either a remarkable coincidence or evidence that Democritus was onto something fundamental about the nature of reality. Either way, it's a reminder that good ideas have a way of resurfacing, even if it takes a couple of millennia and a complete revolution in how we do science. The ancient atomists gave us more than just a theory about what stuff is made of. They gave us a framework for thinking about possibility, infinity, and the limits of existence. They asked questions that we're still trying to answer today using tools they could never have imagined. And they did it all without computers, telescopes, or peer-reviewed journals, just pure human curiosity and the audacity to think that maybe, just maybe, the universe is bigger and stranger than anyone had ever dared to imagine. So the next time you're feeling insignificant in the vastness of the cosmos, remember, some guy in a toga figured this out over 2,000 years ago, probably while eating grapes and laughing at people who still believed everything was made of 4 elements. If Democritus could stare into the infinite void and smile, maybe we can too. Though preferably with a better understanding of dental hygiene, because ancient Greek teeth were not exactly a selling point for the lifestyle. The seeds planted by Leucippus and Democritus would lie dormant for centuries, occasionally sprouting in the writings of later thinkers, but never quite taking root in mainstream thought. The geocentric universe, with Earth at its special centre, dominated Western cosmology for over a millennium. The idea of multiple worlds was considered heretical, dangerous, and frankly a bit rude to God, who had presumably gone to all the trouble of creating this world specifically for us. But ideas, like atoms, have a way of persisting through the void, and eventually someone would come along brave enough or foolish enough to speak these forbidden thoughts out loud. That story, however, is for the next chapter, and spoiler alert, it doesn't end well for the person involved. At least not in this universe. So we've established that ancient Greek philosophers were casually theorizing about infinite universes, while most of humanity was still figuring out bronze. But here's the thing about revolutionary ideas. They have a nasty habit of making powerful people very uncomfortable, and when powerful people get uncomfortable, historically speaking, things tend to get burny. Yes, that's a word now. We're making it a word. The story of the multiverse isn't just written in equations and philosophical treatises. It's written in blood, persecution, and the kind of institutional violence that makes you grateful for modern concepts like freedom of speech and not being set on fire for your opinions. The journey from Democritus's atoms to modern quantum. Theory passed through some of the darkest chapters of human history, and the people who carried these ideas forward often paid the ultimate price for their intellectual courage. Let's talk about Giordano Bruno, a name that should be far more famous than it is, considering he basically died for thinking too hard about space. Born in 1548 in Nola near Naples, Bruno was the kind of person who couldn't stop questioning things even when it was actively dangerous to do so. He joined the Dominican order as a young man, which in retrospect was a bit like a vegan joining a butcher's guild. Not exactly a natural fit for someone who would spend his life challenging religious orthodoxy. Bruno wasn't content with the comfortable geocentric universe that the church had been selling for centuries. You know the one, Earth at the centre, everything revolving around us, humanity as the special pet project of an attentive creator. It was a cosy worldview, really. Flattering even. The cosmic equivalent of being told you're the favourite child. But Bruno looked at this picture and essentially said, "I don't think so." Drawing on the ancient atomist traditions, yes, our boy Democritus makes a comeback, and inspired by the recent work of Copernicus, Bruno proposed something radical. Not just that the Earth orbited the Sun, which was already controversial enough to get you uninvited from all the best dinner parties. No, Bruno went further, much further. He argued that the universe was infinite, that the stars were distant suns with their own planets, and that these planets might harbour life. He essentially described the modern cosmological view of the universe about 400 years before we had the telescopes to confirm it. But wait, there's more. Bruno also suggested that the universe had no centre at all, which meant Earth wasn't just not at the centre, it wasn't even special. Just another rock orbiting another star in an infinite cosmic ocean. This was not exactly the message the Catholic Church wanted to hear in the late 1500s. They had spent considerable effort establishing their authority as the interpreters of God's creation, and here was this annoying friar suggesting that God's creation was infinitely bigger than anyone had imagined, and that we were basically cosmic. Bacteria by comparison. Bruno's personality didn't help matters. He was, by all accounts, not great at making friends or avoiding conflict. He wandered across Europe for years, getting kicked out of one city after another for his controversial views and his apparent inability to keep his mouth shut. He was excommunicated by the Catholics, condemned by the Calvinists, and generally made unwelcome wherever he went. The man had a talent for alienating people that would make even the most provocative social media influencer jealous. In 1592, Bruno made the fatal mistake of returning to Italy at the invitation of a Venetian nobleman who turned out to be less interested in philosophical discussion and more interested in turning Bruno over to the Inquisition. And the Inquisition, as you might guess from the name, was not exactly known for its open-minded approach to intellectual debate. Their idea of hearing both sides was more like hearing your confession before we decide how to punish you. Bruno was imprisoned for 8 years. 8 years of interrogation, isolation and pressure to recant his views. 8 years of being told that the universe was exactly as the church said it was, and if he could just agree to that, everything would be fine. But Bruno, stubborn to the end, refused. When offered a chance to take back his claims about the infinite universe and the plurality of worlds, he reportedly told his judges that they feared pronouncing the sentence more than he feared receiving it, which is an absolutely legendary response, even if it probably wasn't the best legal strategy. On February 17th, 1600, Giordano Bruno was burned at the stake in Rome's Campo de' Fiori. They put a gag in his mouth so he couldn't speak. Apparently even in death they were afraid of his ideas. Today, a statue of Bruno stands in that same square, looking defiantly out at the spot where he was executed. It's become a pilgrimage site for free thinkers and a reminder that ideas really can be dangerous, not because they're wrong, but because they're threatening to those who prefer comfortable lies. Now, Bruno wasn't executed solely for his cosmological views. The charges against him included various heresies, denying core Catholic doctrines, and probably having a bad attitude, which seems to have been his default setting. But his vision of an infinite universe with countless worlds was certainly part of what made him such a threat. He represented a new way of thinking that couldn't be contained by traditional authority, and that made him dangerous in a way that went beyond any specific claim he made. Bruno wasn't alone in suffering for cosmic truth. The history of cosmology is littered with people who were persecuted, silenced, or marginalized for daring to suggest that the universe might be different from what religious authorities claimed. Galileo, born just 4 years before Bruno was executed, would face his own trial by the Inquisition for supporting the Copernican heliocentric model. He was shown the instruments of torture and forced to recant, spending the rest of his life under house arrest. At least he got to keep his life, which was more than Bruno managed. The Church's opposition to new cosmological ideas wasn't purely about astronomy. It was about control. If the universe was infinite and filled with other worlds, what did that mean for human significance? For the special relationship between God and humanity? For the authority of institutions that claimed to speak for that God? Every star with planets was a challenge to the comfortable narrative, and the people in power weren't about to let that challenge go unanswered. But here's the beautiful irony. Burning people for their ideas doesn't actually destroy those ideas. If anything, it gives them power. Bruno became a martyr for free thought, and his vision of an infinite universe filled with countless worlds lived on in the minds of those who came after. You can kill a person, but you can't kill a concept. Ideas are like cosmic background radiation. They permeate everything and persist long after their source is gone. The Church won the battle with Bruno but lost the war with reality. Within a few centuries, the infinite universe would become scientific consensus, and the geocentric model would be a historical curiosity taught in classes about how wrong people used to be. The suppression of cosmological ideas during this period had real consequences for human knowledge. Centuries of potential progress were lost as thinkers learned to keep their more radical ideas private, or couch them in careful language that wouldn't attract inquisitorial attention. Who knows what we might have discovered if the scientific revolution had been allowed to proceed without religious persecution? It's one of those counterfactual questions that's impossible to answer, but depressing to contemplate. Fast forward a few centuries, and the intellectual climate has changed dramatically. The Enlightenment happened, revolutions transformed political systems, and burning people for their mathematical opinions went out of fashion. By the 1800s, scientists and mathematicians could explore radical ideas without quite as much fear of being set on fire, which really did wonders for productivity. Amazing what people can accomplish when they're not worried about becoming a human torch. The 19th century brought a revolution in mathematics that would eventually crack open the door to parallel universes in a way that even Democritus and Bruno couldn't have imagined. This revolution came from an unexpected source: geometry. Specifically, the kind of geometry that made absolutely no sense and violated everything mathematicians had believed for over 2,000 years. To understand why this was such a big deal, we need to talk about Euclid, the ancient Greek mathematician who wrote the book on geometry, literally. His Elements was the geometry textbook for over 2 millennia, and it was based on a set of axioms that seemed so obviously true that questioning them felt almost absurd. One of these axioms, the famous fifth postulate, stated that given a line and a point not on that line, there is exactly one line through that point that never intersects the original line. In other words, parallel lines never meet. Seems reasonable, right? You've probably accepted this since elementary school without giving it a second thought. But here's the thing about axioms that seem obviously true. Sometimes they're not. Sometimes they're just true in the specific context we're used to, and breaking them opens up entirely new realms of possibility. And in the 19th century, several mathematicians independently discovered that you could throw out Euclid's fifth postulate and still get consistent logical geometry. It was just really, really weird geometry. The pioneers of this revolution had names you might not recognize, but absolutely should. Nikolai Lobachevsky, a Russian mathematician who published his work on imaginary geometry in 1829. János Bolyai, a Hungarian who independently developed similar ideas around the same time, and Carl Friedrich Gauss, the mathematical heavyweight who had actually figured this out years earlier, but was too worried about controversy to publish. Gauss, for all his genius, apparently had better survival instincts than Giordano Bruno. What these mathematicians discovered was that you could create perfectly consistent geometric systems where parallel lines behave differently. In hyperbolic geometry, there are infinitely many lines through a point that never intersect a given line. Parallel lines diverge. In elliptic geometry, there are no parallel lines at all. Everything eventually intersects if you extend it far enough. These geometries weren't wrong. They were just different. They described spaces that curved in ways our flat Earth-trained intuitions couldn't immediately grasp. Now you might be thinking, cool, but what does weird math have to do with parallel universes? Patience, dear viewer, we're getting there, and the connection is more profound than you might expect. The discovery of non-Euclidean geometry did something revolutionary to human thought. It proved that mathematics could describe realities that we can't directly perceive or experience. Lobachevsky and Bolyai weren't just playing abstract games with symbols. They were creating mathematical models of spaces that could, in principle, exist, even if we couldn't see them, touch them, or take a vacation there. The numbers worked. The logic was airtight. The only thing missing was physical evidence that such spaces existed anywhere outside the mathematician's imagination. This was a philosophical bombshell. For centuries, mathematicians had assumed that geometry described the space we live in. Euclid's axioms weren't just mathematical conveniences, they were truths about reality. But if there were multiple consistent geometries, which one was real? The answer, it turned out, was far stranger than anyone expected. Enter Bernhard Riemann, a German mathematician who in 1854 gave a lecture that would change everything. Riemann generalized the concept of geometry to include spaces of any number of dimensions with any kind of curvature. His work provided the mathematical framework for describing spaces that curved, twisted, folded, and generally did things that would give a Euclidean geometer nightmares. And crucially, Riemann showed that the properties of these spaces could be described entirely through mathematics, without needing to visualize them or experience them directly. Riemann's geometry sat on the shelf for about 60 years, looking like an elegant but ultimately useless mathematical curiosity. Then Albert Einstein came along, needed a way to describe how massive objects curve the fabric of space and time, and discovered that Riemann had already done the mathematical heavy lifting. General relativity, Einstein's masterpiece theory of gravity, is written in the language of Riemannian geometry. The curvature of space-time that makes planets orbit and light bend around stars is described by equations that trace directly back to those 19th century mathematicians who dared to question Euclid. But the implications went even further. If mathematics could describe curved four-dimensional space-time, why stop there? Why not 5 dimensions? 6? 11? The mathematical tools developed in the 1800s placed no limit on the number of dimensions a space could have. The only constraint was whether the resulting equations were consistent, whether the numbers played nice with each other, and for many configurations of higher dimensional spaces they did. This opened the door to serious scientific speculation about extra dimensions. Maybe our universe, which appears to have 3 dimensions of space and 1 of time, is actually embedded in a higher dimensional reality that we can't directly perceive. Maybe the fundamental forces of nature, gravity, electromagnetism, the nuclear forces, are actually different aspects of a single force operating in higher dimensions. These ideas would eventually lead to string theory and its prediction of 10 or 11 dimensions, but their roots go back to those 19th century rebels who decided that Euclid had been wrong about parallel lines. The connection to parallel universes should now be coming into focus. If mathematics can consistently describe spaces we can't see, and if physical theories suggest that such spaces might actually exist, then the door is open to the possibility that our universe is just one of many, one slice of a higher dimensional reality, one bubble in an infinite foam, one branch of an ever-splitting cosmic tree. The mathematical framework was in place. Now physics just had to catch up, and catch up it did, in the most spectacular and mind-bending ways imaginable. But that's a story for later chapters, when we dive into quantum mechanics and the experiments that broke reality so badly that scientists had to invent parallel universes just to make sense of the data. For now, let's appreciate what the 19th century mathematicians accomplished. They proved that reality doesn't have to follow our intuitions, that the universe might be stranger than we can imagine, and that the right equations can describe worlds we'll never visit but might nonetheless exist. From Democritus's infinite void to Bruno's countless worlds to Riemann's curved dimensions, humanity has been slowly building a mathematical and philosophical case for a multiverse. Each generation added new pieces to the puzzle, often at great personal cost, always pushing against the comfortable certainties of their time. The trail of ideas leads inexorably forward, toward a reality far grander and more mysterious than any single world could contain. And the best part, we're just getting started. Alright, we've travelled from ancient Greece through Renaissance bonfires to 19th century mathematical rebellions. The stage is set, the mathematical tools are ready. Now it's time to enter the 20th century, where physics took one look at common sense, laughed maniacally, and then set it on fire. Not literally, of course. We're past the burning era, remember? But metaphorically, oh, absolutely scorched. The early 1900s brought a series of experiments and discoveries that didn't just challenge classical physics, they mugged it in a dark alley and stole its lunch money. Everything scientists thought they knew about how the universe worked turned out to be, at best, a useful approximation, and, at worst, completely wrong at the smallest scales. Welcome to quantum mechanics, where the rules are made up and your intuitions don't matter. Let's start with the experiment that broke everyone's brain, the double-slit experiment. It sounds simple enough. You take a barrier with two narrow slits in it, you shoot particles at the barrier, and you see what pattern they make on a screen behind it. If particles are like tiny bullets, which is what classical physics would have you believe, they should pass through one slit or the other and create two bands on the screen corresponding to the two openings. Simple, logical, boring. Exactly how physics should be, according to people who enjoy sleeping at night. But that's not what happens, not even close. When scientists performed this experiment with electrons, they got an interference pattern, a series of light and dark bands that spread across the entire screen. This is the kind of pattern you get when waves overlap, with peaks adding together and troughs cancelling out. It's what happens when you drop two stones in a pond and watch the ripples interact. But electrons aren't waves, they're particles. They're supposed to be tiny discrete chunks of matter. So what in the name of rational thought was going on? Here's where it gets truly weird. The interference pattern appears even when you fire electrons one at a time. One single electron shot at the barrier somehow creates an interference pattern over many trials. This means each individual electron is interfering with itself. It's passing through both slits simultaneously, like some kind of subatomic ghost that can't decide which door to use. The electron exists in a superposition of states, a combination of went through the left slit and went through the right slit, until it hits the screen and becomes a definite point. Now, if you're thinking, that can't be right, let me just put a detector at one of the slits to see which way the electron actually goes. Congratulations, you've just discovered the most disturbing aspect of quantum mechanics. When scientists tried exactly that, the interference pattern disappeared. The mere act of observing which slit the electron passed through caused it to behave like a regular particle again, creating just two bands instead of an interference pattern. Let that sink in for a moment. The act of measurement changes the outcome. Not because the detector physically disturbed the electron, scientists got really clever about making non-invasive measurements, but because the information about the electron's path became known. It's as if reality itself refuses to be pinned down, maintaining a cloud of possibilities until someone has the audacity to look, at which point it grudgingly picks one option and commits to it. This is not how respectable physics should behave. This is how a moody teenager behaves. The physicist Richard Feynman, who understood quantum mechanics better than almost anyone, famously said that if you think you understand quantum mechanics, you don't understand quantum mechanics. This wasn't false modesty. This was a genuine acknowledgement that quantum behavior is so contrary to human intuition that truly grasping it might be impossible for brains evolved to track predators and find ripe fruit. We're simply not equipped for this level of cosmic weirdness. But the double-slit experiment was just the beginning. Quantum mechanics kept delivering reality-breaking revelations with the enthusiasm of a conspiracy theorist who just discovered a new documentary. There was the Heisenberg uncertainty principle, which proved that you can't simultaneously know both the exact position and exact momentum of a particle, not because our instruments aren't good enough, but because the universe literally doesn't have definite values for both at the same time. There was quantum entanglement, where particles become correlated in ways that seem to allow instant communication across any distance, which Einstein dismissively called spooky action at a distance, because even geniuses get cranky when physics stops making sense. Each new discovery raised more questions than it answered. If particles exist in superpositions of multiple states, what happens to those other states when we measure one outcome? Do they just disappear? That seems wasteful, cosmically speaking. Do they somehow still exist somewhere? And what exactly constitutes a measurement? Does the universe care whether a human is watching, or would a robot detector be enough? What about a particularly observant cat? The standard interpretation of quantum mechanics, developed primarily by Niels Bohr and his colleagues in Copenhagen, basically told everyone to stop asking awkward questions. According to the Copenhagen interpretation, the wave function, the mathematical description of a particle's superposition of states, collapses when measured, and the particle randomly selects one outcome according to probabilistic rules. Don't ask what happens to the other possibilities. Don't ask what triggers the collapse. Don't ask why observation matters. Just calculate the probabilities and move on with your life. This shut up and calculate approach worked brilliantly for practical purposes. Quantum mechanics became the most accurately tested theory in the history of science, predicting experimental results to absurd levels of precision. But for anyone who cared about what the universe was actually doing, as opposed to just what numbers came out of the equations, the Copenhagen interpretation was deeply unsatisfying. It felt like being handed a recipe for the world's greatest cake, but being told not to ask what ingredients were used or how the oven worked. The quantum world had shattered classical determinism, introduced fundamental randomness into the heart of physics, and left scientists with a mathematical framework that worked perfectly but explained nothing. Something had to give. Something had to make sense of this chaos. And in 1957, a young physicist with a radical idea stepped forward with an answer so outrageous that it made the double-slit experiment look positively mundane by comparison. Hugh Everett III was not your typical physicist. For one thing, he actually enjoyed parties, which already sets him apart from approximately 90% of theoretical physicists throughout history. For another, he was willing to propose an idea so radical that it would get him essentially laughed out of academia, and then he would shrug and go work for the Pentagon instead. The man had range. In 1957, Everett was a graduate student at Princeton, working under the legendary John Wheeler, who was himself a pioneer in quantum physics and general relativity. Everett was supposed to be writing a nice, respectable dissertation on some manageable aspect of quantum mechanics. Instead, he produced a paper that proposed to solve all the interpretational problems of quantum mechanics by suggesting that the universe splits into multiple copies every time a quantum measurement occurs. Just a casual Tuesday in theoretical physics. Everett's insight began with a simple question. Why should the wave function collapse at all? The equations of quantum mechanics, specifically the Schrödinger equation, are perfectly deterministic. They describe how wave functions evolve over time without any sudden jumps or collapses. The collapse was added by hand to match experimental observations, but it was mathematically ugly and conceptually mysterious. What if, Everett wondered, the collapse didn't actually happen? Here's the key move. In the Copenhagen interpretation, when you measure a particle that's in a superposition of two states, say spin up and spin down, the wave function collapses and you get one definite result. The other possibility just vanishes into the philosophical void. But Everett suggested that both outcomes actually occur. The particle goes spin up and spin down. The catch is that each outcome happens in a separate branch of reality. The universe splits, and in one branch you measure spin up, in the other branch you measure spin down. Both versions of you exist, each convinced they got the only result. This sounds absolutely insane, and to be fair, it kind of is. But mathematically it's actually cleaner than the Copenhagen interpretation. There's no mysterious collapse, no special role for observers, no arbitrary distinction between quantum systems and measuring devices. Everything just evolves according to the Schrödinger equation, smoothly and deterministically. The apparent randomness of quantum mechanics isn't random at all. It's just that you can only experience one branch, so from your perspective, the outcome seems unpredictable. The implications of Everett's theory, now known as the many worlds interpretation, are staggering. Every quantum event everywhere in the universe causes reality to branch, and quantum events happen constantly at every level of matter. The number of parallel universes created every second is incomprehensibly large. There are branches where you decided to pause this video 5 minutes ago, branches where you never started watching, branches where you're a completely different person, because some quantum fluctuation in your grandfather's brain led to a different decision that changed your entire family history. In the many worlds picture, every possibility allowed by quantum mechanics is realized somewhere. Every time you make a choice that depends on quantum-level processes in your neurons, which is probably every choice, given how sensitive neural activity is to tiny fluctuations, the universe branches and different versions of you pursue different paths. There's a version of you that took that job, a version that asked out that person, a version that clicked on the cat video instead of this one and is now blissfully ignorant of parallel universes. Naturally, the physics community responded to Everett's brilliant solution with overwhelming enthusiasm and immediate acceptance. Just kidding, they basically ignored him. His thesis advisor, Wheeler, was supportive but urged Everett to tone down the more philosophical implications. The great Niels Bohr, when Everett visited Copenhagen to discuss his ideas, was dismissive and unimpressed. The physics establishment had no interest in multiplying universes when a simple "shut up and calculate" was working perfectly well. Everett was discouraged enough that he essentially abandoned academic physics after getting his doctorate. He went to work as a defense analyst, applying mathematical techniques to military strategy and operations research. He made good money, threw great parties, and rarely discussed quantum mechanics again. The many worlds interpretation seemed destined to become a historical footnote, a clever idea that came too early and shocked too many sensibilities. But ideas, as we've seen, have a way of persisting. Through the 1960s and 1970s, a few physicists kept the many worlds flame alive, most notably Bryce DeWitt, who gave the interpretation its catchy name and worked to popularize it. Slowly, the physics community began to take it more seriously. The mathematical elegance was undeniable, the lack of a collapse postulate was attractive, and as quantum mechanics was applied to cosmology, to the universe as a whole, the Copenhagen interpretation's reliance on external observers became increasingly problematic. Who observes the universe? There's no one outside to collapse the wave function of everything. By the 1990s and 2000s, many worlds had gone from fringe speculation to serious contender. Surveys of physicists showed a significant minority, sometimes a plurality, preferring it over Copenhagen and other interpretations. It became a standard topic in quantum mechanics courses, discussed alongside its competitors rather than dismissed as fantasy. Hugh Everett, who died in 1982 of a heart attack at age 51, never lived to see his vindication. But his idea had finally found its audience. Today, the many worlds interpretation remains controversial but respectable. It has passionate advocates who consider it the only sensible way to understand quantum mechanics, and equally passionate critics who find the multiplication of unobservable universes philosophically extravagant. The debate continues, and there's no consensus on whether Everett was a visionary genius or a brilliant mathematician who took his equations too literally. But here's what's remarkable. An idea born from taking quantum mechanics seriously, from refusing to accept arbitrary collapse rules and mysterious observer effects, led naturally to the multiverse. Everett didn't set out to prove parallel universes exist. He was just trying to make the math work without ugly patches. And the math, followed honestly, pointed toward a reality where every possibility branches into its own world. The multiverse wasn't imposed on quantum mechanics from outside, it emerged from within, as a natural consequence of the theory's own logic. The path from Democritus to Everett is long and winding, but there's a clear thread connecting them. Both started with a basic question about the nature of reality. Both followed their reasoning to conclusions that seemed absurd by the standards of their time. Both proposed that our world is just one among countless others, existing in an unimaginably vast space of possibility. The difference is that Everett had the mathematical framework of quantum mechanics behind him, a framework so successful that dismissing its implications required deliberate philosophical effort. Whether you find the many worlds interpretation compelling or ridiculous, it represents something important: the willingness to take our best theories seriously, even when they lead to uncomfortable conclusions. Science isn't about confirming what we already believe, it's about following the evidence and the math wherever they lead. And sometimes they lead to places stranger than any fiction, to a reality where you exist in infinite variations, making infinite choices, living infinite lives across an infinite branching tree of possibility. That's either the most liberating or the most terrifying thought imaginable. Maybe it's both. In one branch, you're thrilled. In another, you're reaching for the pause button. But in this branch, we're moving forward, because the evidence for parallel worlds doesn't stop with quantum mechanics. There are cosmic clues written in the very fabric of space and time, fingerprints left over from the birth of the universe itself. And that's where we're heading next. We've journeyed through philosophical speculation, mathematical revolution, and quantum weirdness. Now it's time to look up, way up, to the oldest light in the universe and ask whether it carries messages from other realities. Because if parallel universes exist, they might have left evidence, cosmic crime scene evidence. And scientists have been dusting for fingerprints in the most unlikely of places, the faint microwave glow that fills all of space. Let's talk about the cosmic microwave background, or CMB for those who prefer their universe in acronym form. This is the afterglow of the Big Bang, the echo of the moment when the universe went from being an opaque soup of plasma to being transparent enough for light to travel freely. It happened about 380,000 years after the Big Bang, which sounds like a long time but is basically cosmic infancy, the universe learning to walk and immediately face-planting into the furniture of existence. Before this moment, the universe was so hot and dense that photons, particles of light, couldn't travel anywhere without immediately smashing into free electrons. It was like trying to drive through a never-ending snowstorm where every snowflake is made of electricity. Not exactly conducive to visibility. But as the universe expanded and cooled, electrons finally settled down and paired up with protons to form neutral hydrogen atoms. Suddenly, photons could travel freely, and the universe lit up in a blinding flash of radiation. That radiation is still travelling today, almost 14 billion years later. It's been stretched by the expansion of space from its original visible light wavelengths to microwave wavelengths, which is why we call it the cosmic microwave background, and not the cosmic blinding flash of burning your retina's background. This ancient light fills every corner of the observable universe, coming from all directions equally. It's the oldest photograph ever taken, a baby picture of the cosmos from when it was roughly 0.003% of its current age. Now here's the thing about the CMB, it's remarkably uniform. No matter which direction you look, the temperature of this radiation is about 2.7 Kelvin. That's 2.7 degrees above absolute zero, for those keeping track, which makes interstellar space slightly colder than your ex's heart. The uniformity is almost perfect, varying by only 1 part in 100,000 across the entire sky. This smoothness was actually one of the great mysteries of cosmology for decades. How could regions of space that had never been in contact with each other have such similar temperatures? It's like discovering that everyone at a party is wearing exactly the same outfit despite having never met or consulted each other. The answer, as we'll explore in a later chapter, involves something called cosmic inflation, a period of extremely rapid expansion in the very early universe. But for now, let's focus on those tiny variations, those 1 in 100,000 temperature differences that mark the CMB's otherwise smooth complexion. Because those variations are fascinating, and some of them might be very, very strange indeed. In 1992, NASA's COBE satellite produced the first detailed map of the CMB's temperature variations. This was followed by the WMAP mission in the 2000s and the European Space Agency's Planck satellite in the 2010s, each providing increasingly precise measurements. What these missions revealed was a complex pattern of hot and cold spots across the sky, regions where the early universe was slightly denser or less dense, which eventually grew into the galaxies and cosmic structures we see today. Most of these variations fit perfectly with theoretical predictions. The universe, it seemed, had behaved exactly as expected. Most of them, not all of them, enter the cold spot. Located in the southern sky in the direction of the constellation Eridanus, this is a region of the CMB that's colder than it should be. Not by a lot, we're talking about a difference of roughly 70 millionths of a degree, but in a universe where temperature variations are supposed to follow predictable statistical patterns, this cold spot is an outlier. It's like finding a patch of your carpet that's inexplicably damp when the rest of the house is bone dry. Something unusual happened there, and scientists have been arguing about what for nearly 2 decades. The cold spot was first identified in WMAP data in 2004 and confirmed by Planck with even greater precision. It spans about 5 degrees of the sky, which doesn't sound impressive until you realise that the full moon is only about half a degree across. This is a big cold spot. And it's anomalously cold, meaning that when you run statistical simulations of random CMB patterns, you rarely produce a spot this cold and this large in combination. Depending on how you crunch the numbers, the probability of such a spot appearing by chance is somewhere between 1 in 50 and 1 in 200. Those aren't impossible odds, but they're eyebrow-raising. So what could cause an unusually cold spot in the CMB? The The conventional explanation involves something called a supervoid, an enormous region of space with fewer galaxies than average. When CMB light passes through a supervoid, it loses a tiny amount of energy, which would make that region appear colder. In 2015, astronomers did find evidence of a large void in the direction of the cold spot, seemingly confirming this explanation. Case closed, mystery solved, everyone go home, except not everyone was convinced. Some researchers argued that the detected void wasn't big enough or empty enough to fully account for the cold spot's properties. The numbers didn't quite add up. And that left room for more exotic explanations, including one that connects directly to our multiverse story. The cold spot might be a bruise left by another universe bumping into ours. Yes, you read that correctly. Some cosmologists have proposed that if our universe collided with another universe during its early history, back when space was expanding so rapidly that such collisions were theoretically possible, the impact would leave a mark on the CMB. The collision would create a circular or roughly circular region with anomalous temperature properties, depending on the geometry and physics of the impact. The cold spot, with its suspiciously circular shape and statistically unusual coldness, fits this profile uncomfortably well. Now let's be clear, this is speculation, not established science. The supervoid explanation, while imperfect, is still the mainstream favourite. Most cosmologists would bet money on mundane physics over interdimensional cosmic fender benders. But the fact that serious researchers are even considering the collision hypothesis tells you something important. The multiverse has gone from philosophical fantasy to scientific possibility. It's the kind of thing you can now propose in a peer-reviewed paper without being laughed out of the room. That's progress, even if we haven't proven anything yet. The cold spot isn't the only CMB anomaly that has raised eyebrows. There's also the so-called axis of evil, and no, that's not a rejected Marvel villain team, though it absolutely should be. This is a name cosmologists gave to an unexpected alignment in the CMB's temperature patterns. The larger scale variations seem to be oriented along a particular axis that, suspiciously, aligns with the plane of our solar system and the direction of Earth's motion through space. This is weird because the CMB is supposed to reflect conditions in the very early universe, billions of years before our solar system existed. There's no reason cosmic patterns should align with our local neighbourhood unless something very strange is going on. Some scientists think the axis of evil is a statistical fluke or an artifact of how we process the data. Others think it might indicate new physics or even, yes, evidence of other universes. If our universe were part of a larger multiverse structure, with adjacent bubble universes influencing our cosmic neighbourhood, it might leave large-scale imprints on the CMB that appear as mysterious alignments. The universe, in this view, isn't quite as random as it should be, because it's embedded in a larger pattern we can only glimpse the edges of. There are other anomalies too. A slight asymmetry between the northern and southern hemispheres of the CMB, unexplained correlations at certain angular scales, and various statistical quirks that individually aren't conclusive but collectively suggest that maybe, just maybe, our universe isn't as simple as the standard model predicts. Each anomaly has conventional explanations, and each conventional explanation has its critics. The debate continues, fueled by increasingly precise measurements and increasingly sophisticated statistical techniques. What makes the CMB such a powerful tool for multiverse hunting is its antiquity. This light has been travelling since the universe was less than 500,000 years old. It carries information about the earliest moments of cosmic history, before galaxies formed, before stars ignited, before anything we would recognise as structure existed. If parallel universes left marks on our cosmos, they did so very early, and the CMB is our best window into that era. It's like having access to someone's baby photos when you're trying to figure out why they have that weird scar. The search for multiverse evidence in the CMB is ongoing. Future missions, including proposed satellite observatories with even greater sensitivity, will map the CMB's temperature variations and its polarization patterns with unprecedented precision. If there are bubble collision signatures hiding in the data, we might find them. If the anomalies turn out to be statistical noise or mundane astrophysics, we'll learn that too. Either way, the universe is telling us something and we're getting better at listening. But the CMB is just one piece of the cosmological puzzle. The theory that might best explain these anomalies, and that most naturally produces a multiverse as a consequence, is the inflationary model of the early universe. According to inflation, the universe underwent a period of exponentially rapid expansion in its first fraction of a second, smoothing out irregularities and setting the stage for everything that came after. And the strange thing about inflation is that once it starts, it might never completely stop. The result would be not one universe, but an endless foam of bubble universes, each with its own properties, its own history, its own version of the laws of physics. That's a story for the next chapter. But before we go, let's appreciate what the CMB has taught us. This ancient light, invisible to our eyes but detectable by our instruments, carries the memory of the universe's birth. In its subtle patterns, we see the seeds of galaxies and the echoes of primordial physics, and in its anomalies, those stubborn deviations from expectation, we might, just might, be seeing the fingerprints of other worlds. Not conclusively, not yet. But the possibility is there, written in microwaves across the sky, waiting for us to learn how to read it. The universe is speaking. The question is whether we're asking the right questions to understand what it's saying, and whether we're ready for the answers, which might be stranger than anything Democritus or Bruno or Everett ever imagined. But that's the beautiful thing about science. It doesn't care whether we're ready. The truth is out there, cold and ancient and patient, waiting for us to catch up. So let's keep going, deeper into the cosmic mystery, toward the inflationary theory that might explain it all, or at least explain why there's so much to explain in the first place. Remember how we mentioned that the cosmic microwave background is suspiciously uniform, that the universe, in its earliest moments, somehow achieved a temperature consistency that would make a Swiss watchmaker weep with envy? Well, it's time to explain how that happened, and in doing so, we're going to stumble into one of the most mind-bending consequences in all of modern cosmology. Welcome to the theory of cosmic inflation, which started as an elegant solution to some annoying problems, and ended up accidentally predicting infinite universes. Oops, let's set the scene. It's the late 1970s. Disco is dying, Star Wars is dominating the box office, and cosmologists are quietly losing their minds over a few deeply troubling features of the universe. The Big Bang Theory was well established by then. The universe began in a hot, dense state and has been expanding ever since. But the more scientists looked at the details, the more problems they found. These weren't minor issues. These were the kind of problems that keep physicists awake at night, staring at the ceiling and wondering if they chose the wrong career. Problem number 1, the horizon problem. The cosmic microwave background has almost exactly the same temperature in all directions. But here's the thing. Regions on opposite sides of the observable universe were never in contact with each other. There simply wasn't enough time since the Big Bang for light or any other signal to travel between them. So how did these distant regions agree on a temperature? It's like discovering that people on opposite sides of the planet are all wearing identical outfits despite having no communication whatsoever. Either there's a cosmic dress code no one told us about, or something weird happened in the early universe. Problem number 2, the flatness problem. The geometry of our universe appears to be flat or very close to it. In cosmological terms, this means that parallel lines stay parallel, the angles of a triangle add up to 180 degrees, and Euclid was basically right all along. But the universe being flat is actually incredibly unlikely. The equations of general relativity allow for universes that are positively curved, like the surface of a sphere, negatively curved, like a saddle or a Pringles chip, or flat. The flat option is unstable. Any tiny deviation early on would have grown over cosmic time, making the universe either obviously spherical or obviously hyperbolic by now. The fact that we're still flat after 13.8 billion years suggests that the early universe was flat to an absurd degree of precision. We're talking fine-tuning of 1 part in 10 to the power of 60 or so. That's not suspicious. That's a cosmic conspiracy. Problem number 3, the monopole problem. This one's a bit more technical, but basically, certain theories of particle physics predict that the early universe should have produced magnetic monopoles, particles with only a north or south magnetic pole, unlike regular magnets that always have. Both. These monopoles should be everywhere, but we've never found a single one. Where did they all go? Did they get lost? Did they collectively decide to hide from human scientists? The standard Big Bang theory had no good answer. Enter Alan Guth, a young particle physicist at Stanford who in 1980 proposed a radical solution that would solve all 3 problems at once. His idea was simple in concept but staggering in implications. What if, in the tiniest fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion. Not the gradual expansion we observe today, but an explosive growth that would make a nuclear explosion look like a lazy sneeze. Guth called this period inflation, and it would become one of the most important ideas in modern cosmology. Here's how inflation works. Imagine the universe in its first moments is incredibly tiny, far smaller than an atom. Then, driven by a hypothetical field called the inflaton field, physicists are great at naming things clearly, the universe suddenly expands by a factor of at least 10 to the power of 26 in a time span of roughly 10 to the power of minus 36 seconds. That's not a typo. The universe grew by a factor of 100 trillion in less than a trillionth of a trillionth of a trillionth of a second. If you started with something the size of a proton, you'd end up with something several meters across, all in less time than it takes light to cross a single atom. This insane expansion solves the horizon problem beautifully. Before inflation, the entire observable universe was contained in a region so small that light could easily cross it, allowing everything to equilibrate to the same temperature. Then, inflation stretched that tiny uniform region to cosmic scales, preserving its uniformity while blowing it up to the size of the universe we see today. The reason distant parts of the CMB have the same temperature is that they were once neighbours, back before inflation turned a cosmic apartment into a cosmos-spanning empire. The flatness problem solved. Inflation acts like cosmic ironing, smoothing out any curvature in space. Imagine drawing a triangle on a balloon and then inflating the balloon to the size of a planet. The surface would look flat locally, even though it's technically still curved. Inflation does the same thing to the universe, making any initial curvature so stretched out that it's essentially undetectable. We appear to live in a flat universe because we can only see a tiny patch of what might be a much larger, very slightly curved hole, and those pesky magnetic monopoles, inflation dilutes them. If monopoles were produced before or during the very early stages of inflation, the subsequent expansion spreads them out so thinly that you'd expect zero monopoles in the entire observable universe. Problem solved with the elegant simplicity of a theory that basically says we made the universe really, really big, really, really fast, and that fixed everything. Inflation was immediately recognized as a brilliant idea. It was refined by other physicists, including Andre Linde, Paul Steinhardt, and Andreas Albrecht, who developed versions that avoided some technical problems in Guth's original formulation. By the 1990s, inflation was the leading theory of the early universe, and observations of the CMB, particularly its detailed temperature patterns, provided strong evidence that something like inflation actually happened. The theory predicted specific statistical properties in the CMB fluctuations, and the data matched beautifully. But here's where things get really weird, because inflation, followed to its logical conclusions, doesn't just explain our universe. It explains why there should be infinitely many universes, continuously being created in an eternal cosmic foam that makes our entire observable reality look like a single bubble in an infinite champagne ocean. The key insight came from Andre Linde and others who studied what happens when inflation ends. The inflaton field, which drives the exponential expansion, has to decay eventually. That's how inflation stops and normal cosmic evolution begins. But the decay isn't instantaneous or uniform. Different regions of the inflating space can decay at different times, and crucially, some regions might never decay at all. In these regions, inflation continues forever, spawning new regions that may or may not decay, in an endless fractal cascade of cosmic creation. This is eternal inflation, and it's exactly what it sounds like. Inflation that never stops, at least not everywhere. In this picture, our universe is a region where the inflaton field happened to decay about 13.8 billion years ago, ending local inflation and allowing matter, radiation, and eventually galaxies and people to form. But beyond the edges of our observable universe, inflation might still be going on, creating new bubble universes all the time. Each bubble is a separate cosmos, potentially with its own physical laws, its own particles, its own version of chemistry, and maybe even its own version of life. The numbers involved are genuinely incomprehensible. Eternal inflation doesn't produce a large number of universes, or even a very large number. It produces an infinite number, continuously, forever. Every second, though second loses meaning when you're talking about the inflationary multiverse, New bubble universes are being born in the eternally inflating background. Some might be similar to ours. Some might have wildly different physics. Some might exist for barely an instant before collapsing. Some might expand forever without ever producing anything interesting. The variety is literally endless. And here's the kicker. Once you accept inflation as the solution to those early universe problems, which most cosmologists do, eternal inflation follows almost automatically. You have to work hard mathematically to construct inflationary models that don't produce eternal inflation. The default outcome, the most natural prediction of the theory, is an infinite multiverse. Scientists didn't set out to prove parallel universes exist. They were trying to explain why the CMB is so uniform, and they ended up with an infinite factory of cosmic bubbles as a free bonus. Sometimes physics has a sense of humour. The bubble universe picture also connects to those CMB anomalies we discussed earlier. If our universe is one bubble among many in the eternal inflation framework, and if bubbles occasionally collide, those collisions could leave imprints on our CMB. The cold spot, the axis of evil, the various statistical oddities, some cosmologists think these might be bruises from ancient bubble collisions, moments when our infant universe bumped into a neighbour in the cosmic foam. It's speculative, but it's the kind of speculation that follows naturally from taking inflation seriously. Of course, there are skeptics. Some physicists argue that eternal inflation, while mathematically interesting, produces a multiverse that's fundamentally untestable and therefore unscientific. If we can never observe other bubble universes, if we can never prove they exist, are we doing physics or philosophy? This is a genuine concern, and it fuels ongoing debates about the nature of scientific explanation and the boundaries of empirical inquiry. The multiverse isn't universally accepted, pun absolutely intended, but it's also not easily dismissed. What makes eternal inflation so compelling is that it wasn't invented to explain the multiverse. It was invented to explain observable features of our own universe, and the multiverse emerged as an unexpected consequence. This is how good theories often work. They explain what you were trying to explain and then surprise you with additional predictions you never anticipated. General relativity predicted gravitational lensing and black holes before anyone observed them. Quantum mechanics predicted antimatter before anyone found it. And inflation predicts a multiverse, whether we're ready for that or not. The universe factory never closes. Somewhere beyond everything we can see, new bubbles are forming, new realities are emerging, new laws of physics are being instantiated. Our entire observable universe, every galaxy, every star, every planet, every atom, is just one instance in an infinite ensemble. We're not even special in our uniqueness, because in an infinite multiverse, there are infinite universes arbitrarily similar to ours, and infinite universes wildly different. Everything that can happen does happen somewhere in some bubble, in the endless foam of eternal inflation. This is either the most liberating or the most terrifying idea in cosmology. Maybe both. But before we get too lost in the multiverse, let's zoom in on another theoretical framework that also demands extra dimensions and multiple universes: string theory. Because as it turns out, the mathematicians trying to unify all the forces of nature found themselves accidentally predicting a landscape of possibilities that makes eternal inflation look almost modest by comparison. And that's saying something. So far we've seen how quantum mechanics accidentally suggested branching universes, how inflation naturally produces bubble cosmoses, and how the CMB might carry scars from cosmic collisions. But we haven't yet discussed the theoretical framework that takes the multiverse idea and cranks it up to 11, and then keeps cranking until the dial breaks off. Welcome to string theory, where the number of possible universes isn't just large, it's so absurdly, incomprehensibly vast that it makes infinity feel almost cozy by comparison. String theory began with a noble goal: to be the theory of everything. For decades, physicists have been haunted by the fact that our two best theories of reality, general relativity, which describes gravity and the large-scale structure of space-time, and quantum mechanics, which describes everything else at the smaller scales, don't play nice together. Try to combine them mathematically, and you get infinities popping up everywhere, equations that spit out nonsense, and theoretical physicists developing stress-related eye twitches. The universe clearly runs on both theories simultaneously, but our math kept insisting they were incompatible. Not exactly a confidence-inspiring situation. String theory offered a potential solution. Instead of treating fundamental particles as point-like objects with no size, string theory proposed that everything is made of tiny, vibrating strings of energy. Different vibration patterns produce different particles, much like different vibrations of a guitar string produce different musical notes. Gravity, electromagnetism, the nuclear forces, all would emerge from different modes of these fundamental strings. One framework to rule them all, one theory to explain the universe, elegant, beautiful, and promisingly mathematical. There was just one small catch. For the math to work, string theory required extra dimensions. Not one extra dimension, not two. Depending on the version, string theory needs either 10 or 11 dimensions of space-time. We experience 3 dimensions of space and 1 of time, which means there are 6 or 7 additional dimensions that we somehow don't notice. Where are they hiding? The standard answer is that they're compactified, curled up so small that we can't detect them. Imagine an ant walking on a garden hose. From the ant's perspective, there are 2 dimensions, along the hose and around it. But from far away, the hose looks like a one-dimensional line because its circular dimension is too small to see. String theory's extra dimensions are supposedly like that, just way smaller, on the order of the Planck length, about 10 to the power of minus 35 meters, which is to an atom what an atom is to the observable universe. Now, compactified dimensions might sound like a convenient cop-out, but they're actually crucial to how string theory connects to the physics we observe. The shape and size of those curled-up dimensions determine what particles exist, what forces operate, and what the fundamental constants of nature are. Different compactifications produce different physics. And this is where the multiverse enters with the subtlety of a freight train. In the early days of string theory, physicists hoped that the mathematics would uniquely determine how the extra dimensions must be shaped. There would be one correct compactification, one set of physical laws, one universe that string theory predicts. This would be the ultimate vindication of the theory. It would tell us not just that reality is made of strings, but exactly what kind of strings configured in exactly what way, leaving no room for alternatives. That was the dream. The dream died hard in the early 2000s. Instead of finding one unique solution, string theorists discovered what's now called the landscape, an enormous space of possible compactifications, each corresponding to different physics. How enormous! Current estimates suggest the landscape contains around 10 to the power of 500 distinct possibilities. That's a 1 followed by 500 zeros. For context, the number of atoms in the observable universe is roughly 10 to the power of 80. The number of possible chess games is around 10 to the power of 120. The number of seconds since the Big Bang is about 10 to the power of 17. We're talking about a number so large that it makes every other large number in physics look like a rounding error. Each point in this landscape represents a different way the extra dimensions could be compactified, and each compactification produces a different universe, with different particles, different forces, and different physical constants. Some of these universes might have gravity but no electromagnetism. Some might have 17 types of quarks instead of 6. Some might have forces we can't even imagine operating in ways that would make our physics textbook spontaneously combust. The variety is essentially unlimited. String theorists initially reacted to the landscape with something between dismay and existential crisis. This wasn't supposed to happen. The theory of everything was supposed to explain why the universe is the way it is, not shrug and say, well, it could have been any of these 10 to the power of 500 options, take your pick. Some physicists argued that the landscape was a sign string theory had. Failed that a theory predicting everything predicts nothing. Others pointed out that we hadn't actually derived the landscape rigorously yet, that future mathematical developments might dramatically reduce the number of possibilities. But a third group, led by figures like Leonard Susskind and others, embraced the landscape and proposed a radical reinterpretation. What if the landscape isn't a bug but a feature? What if all those 10 to the power of 500 possibilities aren't just mathematical abstractions, but actual universes that exist somewhere in the eternal inflation framework? Combine string theory's landscape with eternal inflation's bubble universes, and you get a picture where every possible compactification is realized in some bubble somewhere. The multiverse isn't just big, it's the ultimate expression of cosmic diversity, containing every possible version of physics that string theory allows. This synthesis of string theory and eternal inflation is sometimes called the string landscape multiverse, or simply the megaverse, because apparently multiverse wasn't grandiose enough. In this picture, our universe is one bubble among infinitely many, and the specific physics we observe, the particular particles, forces, and constants, are determined by which random point in the landscape our bubble happened to land on. It's cosmic roulette with 10 to the power of 500 slots, and we won, or lost, depending on your perspective, the particular combination that allows atoms and stars and planets and YouTube videos to exist. The landscape multiverse is controversial, to put it mildly. Critics argue that it's untestable. We can never visit other bubbles, never directly observe different physics, never verify that the landscape actually contains what string theorists claim. If the theory can explain any possible observation by pointing to some corner of the landscape, does it really explain anything? This is a legitimate philosophical concern, and it's sparked intense debates about what counts as science versus speculation. Supporters counter that the landscape might make statistical predictions. If we understand how bubbles are created and how likely different compactifications are, we might predict what typical observers should see and check if our observations match. This anthropic reasoning, which we'll explore in the next section, offers a potential way to extract testable consequences from an apparently untestable framework. The jury is still out on whether this approach will succeed. What's remarkable about the string landscape is how it transforms the question, why does the universe have the properties it does? Instead of looking for a fundamental reason, some deep principle that makes our physics inevitable, the landscape suggests there might be no reason at all. Our universe has the properties it does because those are the properties of the particular landscape point we happen to inhabit. In another bubble, with another compactification, everything would be different. We're not special, we're just one option among an incomprehensibly vast menu of cosmic possibilities. Whether the string landscape is real, or a mathematical mirage remains to be seen. String theory itself has never made a testable prediction that's been verified, which is a significant weakness for any scientific theory. But even as speculation, the landscape illustrates something profound. Our best attempts to find a unique theory of everything keep leading us to infinite diversity instead. The universe seems to resist being pinned down to a single explanation, and that might be telling us something important about the nature of reality, or about the limits of our theories to capture it. Let's take a step back from the theoretical stratosphere and look at something concrete. The actual numbers that describe our universe. The speed of light, the strength of gravity, the mass of an electron, the charge of a proton. These fundamental constants determine everything about how matter behaves, how stars burn, how chemistry works, and whether anything interesting can happen at all. And here's the disturbing part. These numbers appear to be fine-tuned with almost miraculous precision to allow life to exist. Consider gravity. We all know gravity. It's the force that keeps us from floating off into space and makes dropping your phone such a tragedy. The strength of gravity is determined by a number called Newton's gravitational constant. If you tweak that number, even slightly, the consequences are catastrophic. Make gravity a bit stronger, and stars burn through their fuel too quickly, exploding before planets can form or life can evolve. Make it a bit weaker, and matter never clumps together enough to form stars in the first place. The universe becomes a thin, cold soup of particles spreading forever into the void. Neither scenario includes you watching this video, because neither scenario includes you. Now consider the strong nuclear force, which holds atomic nuclei together. This force has to be precisely calibrated for carbon atoms to exist. Carbon, you may recall, is kind of important for life as we know it. It's the backbone of organic chemistry, the basis of DNA, the reason you're made of something more interesting than hydrogen gas. The production of carbon in stars depends on a delicate nuclear resonance that exists only because the strong force has exactly the strength it does. Change it by a few percent, and carbon doesn't form. No carbon, no organic molecules, no life. Not even the simple stuff. The electromagnetic force, which governs how charged particles interact, has similar constraints. Too strong, and electrons get bound too tightly to atoms, preventing the chemistry needed for life. Too weak, and atoms become too loosely bound, falling apart at the slightest provocation. The ratio between electromagnetic and gravitational forces is about 10 to the power of 36 to 1. Gravity is incredibly weak compared to electromagnetism. If that ratio was significantly different, the universe would be unrecognizable and almost certainly lifeless. And it's not just the forces. The masses of fundamental particles, the number of spatial dimensions, the expansion rate of the universe, the initial density fluctuations that seeded galaxy formation, all of these appear tuned within narrow ranges that permit complexity. The cosmological constant which governs the expansion of the universe is famously fine-tuned to about 1 part in 10 to the power of 120. If it were much larger, the universe would have expanded so fast that no structures could form. If it were significantly negative, the universe would have collapsed back on itself almost immediately. We exist in a Goldilocks zone of cosmic parameters, where everything is just right for stars, planets, chemistry, and eventually beings capable of asking why everything is just right. This is the fine-tuning problem, and it has haunted physicists and philosophers for decades. There are basically 3 possible responses, and each has profound implications for how we understand reality. Option 1. Cosmic coincidence. Maybe we just got lucky. The constants are what they are for no particular reason, and we happen to exist in a universe where they permit life. This is logically possible, but emotionally unsatisfying. It feels like shrugging at the most important question you could ask. The odds of randomly landing on life-permitting parameters seem impossibly small, though of course probability calculations about something we only observe once are philosophically tricky. Option 2. Intelligent design. Maybe the constants were set deliberately by some cosmic designer who wanted life to exist. This is the religious or deistic interpretation, and it has obvious appeal if you're inclined towards such worldviews. The universe looks designed because it was designed. Science can't really address this option directly. It's outside the scope of empirical inquiry, but it remains popular among those who find naturalistic explanations unsatisfying. Option 3. The multiverse. And here's where everything we've discussed comes together. If there are infinitely many universes with different physical constants, whether from eternal inflation, the string landscape, or some combination, then it's not surprising that we find ourselves in one where life is possible. We couldn't find ourselves anywhere else. Universes with the wrong constants don't produce observers to notice how wrong they are. This is the anthropic principle in action. We observe a fine-tuned universe because only fine-tuned universes produce observers. The anthropic explanation of fine-tuning is elegant in a certain way. It doesn't require luck or design, just vast cosmic diversity plus the obvious fact that we can only exist where existence is possible. It's like asking why the Earth happens to be at just the right distance from the Sun for liquid water. The answer isn't that Earth was placed there deliberately, or that we got incredibly lucky. The answer is that billions of planets exist at various distances from their stars, and life only evolved on one, or more, where conditions were right. We observe a habitable planet because we couldn't have evolved on an uninhabitable one. The multiverse applies the same logic to the universe as a whole. Critics of the anthropic multiverse argument point out that it can feel like a cop-out. Instead of explaining the constants, it just pushes the question back. Why is there a multiverse? Why does it have the particular distribution of constants that it does? And is invoking unobservable universes really better than invoking an unobservable designer? These are fair objections, and the debate continues. But the anthropic argument does make specific predictions. For instance, that the cosmological constant should be small but probably not zero, which matches observations, lending it at least some empirical credibility. What's philosophically fascinating is that the fine-tuning problem forces us to confront the nature of explanation itself. Do we want to explain why the constants have their specific values, or are we satisfied explaining why some universe somewhere has life-permitting values? These are different questions with different answers, and which one you find meaningful depends on your philosophical temperament as much as your scientific commitments. The multiverse, for all its strangeness, offers a framework where fine-tuning isn't a miracle or a mystery, but a selection effect. We see a life-permitting universe because that's the only kind of universe we could see. The vast majority of cosmic real estate might be sterile, empty, governed by physics that permits nothing interesting. But we're not there. We can't be there, so we'll never know about it directly. Our cosmic neighborhood is one bubble in an infinite foam, one compactification in a 10 to the power of 500 landscape, one branch of an eternally splitting quantum tree. And in all that diversity, there's at least one corner where atoms form, chemistry happens, stars shine, and conscious beings emerge to ask why any of this exists at all. that might not be the answer we wanted. We might prefer a universe that's unique and necessary, where everything exists for a reason and our presence is cosmically significant. But science doesn't always give us what we want. It gives us what's true, or at least what's consistent with the evidence. And increasingly, the evidence points toward a reality far vaster, stranger, and more indifferent than our ancestors ever imagined. A reality where we're neither central nor necessary, but nonetheless here, asking questions, seeking understanding, and marveling at the improbable fact of our own existence. The fine-tuning problem doesn't have a final answer yet. But whatever the answer turns out to be, coincidence, design, or multiverse, it will tell us something profound about our place in reality. And that's worth thinking about, even if the thinking leads somewhere uncomfortable, especially then. We've travelled an extraordinary distance in this video. From ancient Greek philosophers pondering atoms in the void, through martyrs burned for cosmic heresy, past mathematical revolutionaries and quantum weirdness, into the inflationary foam of bubble universes and the incomprehensible landscape of string theory. The evidence points toward a multiverse. The mathematics demands it. The finest minds in physics take it seriously. But here's the uncomfortable question we've been dancing around. Can we ever actually prove any of this? Or are we just telling ourselves sophisticated stories that happen to make the equations prettier? This is the elephant in the cosmological room, and it's time to stare directly at it. The most common criticism of multiverse theories, whether quantum many worlds, eternal inflation, or the string landscape, is that they're fundamentally untestable. If other universes exist beyond our cosmic horizon, forever inaccessible to observation, what's the difference between saying they exist and saying unicorns live on the far side of reality? Both claims are equally impossible to verify. Both require faith in things we can never see, and faith, however dressed up in mathematical notation, isn't science. Or so the critics argue. This criticism has real teeth. Science, at its core, is supposed to be empirical. We make hypotheses, we test them against observations, we discard the ones that don't match reality. That's what separates physics from philosophy, astronomy from astrology, chemistry from alchemy. If a theory makes no testable predictions, if there's no conceivable observation that could prove it wrong, then it exists in a strange limbo, mathematically interesting perhaps, but scientifically meaningless. And the multiverse, on the surface, seems to be exactly that kind of theory. Think about it. The other branches in Everett's many worlds interpretation are, by construction, completely isolated from our own. You can never meet your quantum alternate selves, never send messages to other branches, never detect their existence directly. The bubble universes of eternal inflation are separated from us by regions of still inflating space that expand faster than light can travel. They're not just far away, they're fundamentally unreachable, receding from us faster than any signal could. Ever bridge the gap. The 10 to the power of 500 compactifications of string theory exist as mathematical possibilities, but we can only ever observe one, our own. How do you test a theory when 99.999% of its predictions are permanently hidden from view? Some physicists have thrown up their hands and declared the multiverse unscientific, not necessarily wrong, just outside the bounds of what science can address. Paul Steinhardt, one of the original architects of inflationary theory, has become a vocal critic, arguing that a theory that predicts everything predicts nothing. If any observation is compatible with some corner of the multiverse, then no observation can ever rule the multiverse out, and a theory that can't be ruled out can't be confirmed either. It just sits there, unfalsifiable and untouchable, like a cosmic conspiracy theory with really good mathematics. But not everyone agrees with this pessimistic assessment. A growing number of physicists argue that the multiverse, while challenging, isn't necessarily beyond the reach of science. The key is to think creatively about what counts as evidence. We might not be able to visit other universes, but we might be able to detect their indirect effects on our own. We might not be able to test every prediction of the multiverse, but we might be able to test statistical predictions about what typical observers should see. The game isn't over, it's just more subtle than we're used to. Let's talk about some of the ways scientists are actually searching for multiverse evidence right now, with real instruments and real data. First, there's the cosmic microwave background, which we discussed earlier. If our bubble universe collided with another bubble early in cosmic history, that collision might have left a circular imprint on the CMB, a region with anomalous temperature or polarization properties. Several research teams have developed algorithms to search for such signatures in the Planck satellite data. So far, no definitive detection, but the search continues. Future CMB experiments with even greater sensitivity might find what current ones have missed. A single clear bubble collision signature would be extraordinary evidence that other bubbles exist, that the multiverse is real and has actually touched our universe. Second, there are gravitational waves. The cosmic inflation that spawned our universe should have produced a background of gravitational waves, ripples in space-time itself, that permeate the entire cosmos. The specific pattern of these primordial gravitational waves depends on the details of how inflation worked, and different inflationary models make different predictions. If we detect primordial gravitational waves, which several experiments are actively trying to do, their properties could tell us whether our inflation was the kind that naturally produces eternal inflation and bubble universes. It's indirect evidence, but it's evidence nonetheless. Third, there's the distribution of matter in the universe. If our universe is embedded in a larger multiverse structure, there might be subtle statistical anomalies in how galaxies are distributed, how the cosmic web is organized, or how the universe's large-scale properties vary from region to region. Some of the CMB anomalies we discussed, the cold spot, the axis of evil, could be hints of this kind. Upcoming surveys, mapping billions of galaxies with unprecedented precision, will give us far better data to look for such patterns. The James Webb Space Telescope, the Vera Rubin Observatory and future missions will transform our understanding of cosmic structure and might reveal hints of physics beyond our standard models. Fourth, there's the possibility of detecting quantum signatures that support the many worlds interpretation specifically. While we can't directly observe other branches, some physicists have proposed experiments that could distinguish many worlds from competing interpretations of quantum mechanics. These involve subtle tests of quantum coherence, interference patterns, and the behavior of quantum systems under measurement. If many worlds is correct, certain experiments should give different results than if Copenhagen-style collapse is correct. These experiments are extremely difficult at the edge of current technology, but they're not impossible in principle. Fifth, and this is more speculative, there's the idea that information might somehow leak between universes. If the multiverse has structure, if bubble universes can influence each other even after separation, there might be detectable consequences. Some theorists have proposed that the constants of nature in our universe encode information about neighbouring universes, like fingerprints left by cosmic siblings. This is highly speculative, but it illustrates how creative physicists are getting in their search for multiverse evidence. Beyond direct detection, there's another way the multiverse might prove its worth: by making successful predictions about our own universe. The anthropic reasoning we discussed, that we observe life-friendly constants because we couldn't observe anything else, actually makes quantitative predictions. It predicts that the cosmological constant should be small but not zero, because only a narrow range allows galaxy formation, and smaller values within that range are more probable. When the cosmological constant was measured in 1998, it turned out to be exactly in the range the anthropic multiverse predicted. That's not proof, but it's suggestive. A theory that makes correct predictions deserves to be taken seriously, even if its other predictions are harder to test. The debate over whether the multiverse is scientific or not ultimately comes down to philosophy of science, to questions about what science is, what evidence means, and how we should reason under uncertainty. These are important questions, and honest scientists can disagree about them. But it's worth noting that many of our best theories were considered untestable when first proposed. Atoms were philosophical speculation for millennia before we could confirm their existence. Black holes were mathematical curiosities before we detected gravitational waves from their mergers. The multiverse might follow the same trajectory, currently at the edge of testability, but gradually becoming accessible as our instruments and understanding improve. What's clear is that the question isn't closed. Scientists aren't just sitting around debating philosophy. They're building experiments, analysing data, and searching for signs that other universes are real. They might fail. The multiverse might remain forever beyond our reach. But they're trying, and that's what science is supposed to do: push against the boundaries of the knowable, even when success isn't guaranteed, especially then. The universe has a long history of being stranger than we expected and more accessible than we feared. From atoms to galaxies, From quantum fields to gravitational waves, discoveries that seemed impossible have become routine. Maybe the multiverse will join that list, or maybe it won't, and future physicists will look back at our multiverse obsession the way we look back at phlogiston and luminiferous ether, interesting detours on the road to deeper truth. Either way, the search itself is valuable. It's how we learn, it's how we grow, it's how we become worthy of the questions we dare to ask. So here we are, at the end of our journey through the multiverse. We've crossed millennia of human thought, from Democritus's atoms dancing in infinite void to Everett's branching quantum worlds, from Giordano Bruno's infinite cosmos to the 10 to the power of 500 possibilities of string theory's landscape. We've seen the CMB's ancient light, potentially carrying bruises from bubble collisions. We've grappled with the fine-tuning problem and the anthropic principle. We've stared into the abyss of untestability and watched scientists light candles against the darkness anyway. If the multiverse is real, and the evidence is mounting even if it's not yet conclusive, then reality is vaster than anything our ancestors could have imagined. Our entire observable universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, is just one bubble in an infinite foam, one branch on an endlessly splitting tree, one compactification among 10 to the power of 500 possibilities. We are small, cosmically speaking, insignificant in scale, a single note in an infinite symphony that no one can hear in its entirety. And yet, here's the thing about infinity that's easy to forget. Being one among infinitely many doesn't make you less real. It doesn't make your experiences less meaningful. It doesn't diminish the fact that you, specifically you, watching this video in this universe at this moment, are having this experience. No one else is having exactly this experience. Not even the other versions of you that might exist in other branches, other bubbles, other compactifications. They're having their experiences different in ways subtle or profound. But this one is yours, only yours, forever. The multiverse, paradoxically, doesn't reduce your significance, it highlights it. In a single, finite universe, your uniqueness might seem like an accident, a random configuration of atoms that happen to achieve consciousness. But in an infinite multiverse, your existence is a mathematical certainty. Given infinite trials, everything that can happen must happen somewhere, and you is something that can happen. You're not an accident, you're an inevitability. The multiverse guaranteed your existence the moment it permitted it. But here's the deeper point. Even if infinite versions of you exist, scattered across infinite realities, making infinite choices, they're not you. They don't share your memories, your relationships, your specific history. They diverged at some quantum branch point and went their own way. The version of you that asked out that person and the version that didn't, they're not the same person anymore. They can't be. They've had different experiences, formed different memories, become different selves. Identity isn't about atoms, it's about pattern, continuity, narrative. And your narrative is yours alone. This might seem like philosophical hair-splitting, but it matters. One of the most common anxieties about the multiverse is that it makes everything meaningless. If every choice leads to every outcome somewhere, why does any choice matter? If there's a version of you that becomes a saint and a version that becomes a monster, does it even matter which one you become? The answer, I think, is yes. It matters enormously. Because you're not choosing for all your alternate selves, you're choosing for you. The version of you in this branch, living this life, facing these consequences. Your choices shape your reality, your relationships, your character. The multiverse doesn't rob you of agency. It multiplies the arenas in which agency operates. Think of it this way. If you're playing a video game and you know there's a parallel universe where you made the other choice, does that make your current playthrough meaningless? Of course not. This is the one you're experiencing, this is the story you're living. The existence of other stories doesn't erase yours. If anything, it makes the concept of story richer. There's not just one narrative, but infinite narratives, each valid, each real, each deserving of engagement. The multiverse also offers a strange kind of comfort. Every path not taken, every opportunity missed, every loved one lost. Somewhere, in some branch, things went differently. The relationship that ended badly, there's a universe where it worked out. The career you didn't pursue, there's a version of you who did. The words you never said, Somewhere, some version of you said them. This doesn't change your reality, but it might change how you feel about regret. Not everything that could have been has been lost. It just exists elsewhere, in branches you can't visit but can imagine. The multiverse is a reservoir of possibility, a reminder that the space of what's real is far larger than the space of what any one observer experiences. And for those who find the multiverse terrifying, the vastness, the insignificance, the endless proliferation of realities, I'd offer this. You were always part of something vast. The universe was always bigger than you could comprehend. Adding more universes doesn't change your relationship to infinity. It just makes the infinity more interesting. And maybe, just maybe, it makes our existence more wonderful. We're not isolated specks in an empty void. We're connected to an infinite web of possibility, each branch exploring some aspect of what reality can be. We're part of something grand, even if we can only experience our tiny corner of it. The ancient Greeks stared up at the stars and wondered if there were other worlds out there. Giordano Bruno went to the flames defending the idea of infinite cosmic diversity. Hugh Everett proposed splitting realities and was laughed out of physics. But the idea persisted, evolved, found new mathematical homes and new observational possibilities. The multiverse is humanity's oldest cosmic intuition, dressed up in the language of modern science. We've always suspected we weren't alone in existence. Now we have reasons, not proof, but reasons, to think we were right. So what do you do with this knowledge? How do you live in a multiverse? I think you live exactly as you always have, with curiosity, with kindness, with attention to the moments that make up your specific existence. You cherish your relationships, knowing that they're unique even if variations exist elsewhere. You make your choices carefully, knowing that they matter for the you that's making them. You stay curious about the cosmos, knowing that the answers are still out there, waiting to be discovered by minds that haven't given up asking. The multiverse doesn't diminish you, it contextualizes you. It places you in a vast tapestry of existence that stretches beyond imagination, filled with versions of reality we can barely conceive. And in all that infinity, there's only one you, this you, here, now, experiencing this moment. That's not nothing. That's everything. That's the whole point. Thank you for joining me on this journey through the parallel worlds. If you made it this far, you're clearly someone who loves going deep into these cosmic questions, and I appreciate that more than you know. If you enjoyed this video, hit that like button. It really helps the channel. Subscribe if you want more content like this, and drop a comment telling me your thoughts. Do you think the multiverse is real? Does the idea inspire you or terrify you? I'd love to hear your perspective. Until next time, stay curious. And remember, somewhere in the multiverse there's a version of you who didn't watch this video, but this version did, and that makes all the difference.